Most conversations about AI in software development revolve around a single point: the better prompt. Write a smarter prompt, get better code. And for a single task, that's actually true. But the moment you want to seriously build AI into a professional development workflow, hundreds of units, tasks spanning several days, several sessions at once, several projects at once, you hit a wall that no prompt in the world can break through. But first, let's roll the intro. Welcome to my very first session on working with AI and the tools you need to do it. If you don't know me, my name is Frank Lauter. I've been a Delphi developer since the very first days of Turbo Pascal, and I'm an Embarcadero MVP. If you found my YouTube channel, you probably also know my homepage, www.delphiprofi.com, and my blog. So let's dive straight into today's little excursion into the world of AI. This isn't a theoretical lecture about AI. It's a toolbox that I use in production and offer commercially. Today I'll show you how it works, and you decide where it becomes interesting for you. The thread running through all of it is this staircase, 14 steps. Step by step, you'll see why the next one is the natural improvement and extension of the one before. At the very bottom, copy and paste in the browser. At the very top, a backend where AI agents work like real team members. My job isn't just to ease your way up to the next step, it's to show you why you won't want to stay where you are, and why you'll want to climb higher. By the time we reach the top, you probably won't understand yourself why you ever worked in the browser at all. Let's start at the very bottom. Everyone knows the foundation. You've got a chat window open in your browser, you paste in some code, ask a question, you get an answer, and paste the result back into the IDE. And for a small task, that's perfectly fine. It works, but let's look at where it breaks down once things get serious. The agent has to rewrite the entire unit every time, and then you paste the code into the editor. Or maybe you'd rather paste it into Beyond Compare first to see what the agent actually changed in that unit. Apart from the time it takes to generate, after 4 or 5 round trips, you'll notice that errors you already fixed on trip 2 are showing up again. That's because the agent always has to rewrite the unit from memory, and mistakes creep in along the way. Or the agent hands you the parts it changed as code blocks. In fact, it's even worse. You then have to spend ages figuring out where that snippet belongs. And whether the code even compiles is a whole different question. I bet there's at least one unit missing in the uses clause. Why is that? First, the agent has a poor memory, and it gets worse the longer the conversation goes on. That architecture decision from last week? Forgotten. Second, he can't touch anything. The agent only sees the text you hand him. He can't compile, can't look into your other units, can't check whether his suggestion even builds. Third, and this is the real crux, you are the bridge. Every piece of context the agent needs, you have to copy back and forth by hand. With one file, that's doable. With a unit of 2,000 lines that depends on 30 other units, that's exactly what turns it into a full-time job. That's the foundation, and the way out isn't a better prompt. The way out is, give the agent access to your code. A quick aside, this video turned out a bit longer than planned, and there are 2 reasons for that. First, at an event, so many AI questions came up that I saw there's still a real need to talk about it. And second, on the internet, someone claimed I probably have no clue about AI at all. I hope you'll watch it through. There's also a really nice demo hidden at the end that you probably don't want to miss. And this is most likely just part 1. There may be a second video where I explain how this one was made, and the third will surely be an update, because between the idea for this video and today, 4 weeks have already passed, and in the world of AI, that's an eternity. Naturally, new modules and MCP servers have appeared in those weeks already. On stage 1, we leave the browser. The agent now runs as a console app directly on your machine. The difference from the browser, the agent now has direct access to your file system. He can read units and other files himself, so there's nothing left for you to copy over. That sounds like a small step, but it's the first step in the right direction. Personally, I prefer a console window. Nothing is hidden, and I can see exactly what the agent is doing. That's already a noticeable difference. You no longer have to copy code around, but the agent still doesn't have access to real tools. He can read and write files, but everything else he has to piece together by himself through the command line. Compiling, he can give it a try by calling the compiler by hand, but that's not reliable, and the memory problem is still there anyway. You're no longer the bridge for the code, but you're still the bridge for everything else. Actually, I just realized, of course you don't enter a slash in a command, but it's a good example that the AI doesn't always do everything perfectly. It's perfectly understandable if you don't fully trust the whole thing at first. So you put the agent into a mode where he asks for permission every single time. Either you have incredible patience, or you switch that mode off after 5 minutes tops. By the 20th prompt asking whether he may use a tool or read something from disk, you've stopped checking what the agent wants you to confirm anyway. It's a lot like the admin rights dialog in Windows. We know it's coming, especially when we want to install something, but we have to confirm it anyway, so we just click OK. You've taken the first step, away from the browser, toward working directly with files. Whatever model you use, he finds his way around your drive pretty quickly, if you let him. After a few tries, he figures out which Delphi version you're on and where to find MS-build. He might even realize he has to call rsvars first, but at the latest, when he takes 4 tries and still gets it wrong, it starts to grate. We need tools. On stage 2, the agent gets real tools. A well-known example is Kai, a plugin that runs right inside the Delphi IDE and lets the agent compile, generate forms, and access the project tree. What Kai gives you is not just file access. These are real tool calls. Without Kai, your agent needs a bit of help to do the same from the console. The technical foundation for this is called MCP, the Model Context Protocol. Simplified, a standardized way for an AI agent to call functions, only the ones we give him, of course. A tool might be, read this file, compile this project, search the source code. The AI calls the tool, gets a real result, and keeps working with it. It's no longer blind, and no longer has to read everything line by line. I offer exactly these individual MCP servers, for example, for working with Delphi source code, for Word documents, for Outlook, for Jira. Each one covers exactly one area. The source code is available, a good starting point if you want to understand how something like this can be implemented in Delphi. More on that at the end. This feels like a huge leap, and it is. Depending on which service you use, you have a limited number of free actions or tokens. Some call them credits. It really just means you can't use the agent without limits. Once your limit is used up, you can either wait or buy more credits. Since Kai uses the same AI services, that applies to him too, of course. A second key decision is which model to use. Models differ significantly in capability and, of course, in cost. Stronger models are more expensive than weaker ones. Beyond the model itself, there is also the effort setting. It controls how much reasoning budget the model may use before producing an answer. Higher effort can improve quality, especially for complex tasks, but it also increases latency and cost. At this stage, you can already get quite far, and once you discover that with the right prompt, you can get the agent to spin up several sub-agents in parallel, hunting down a bug or implementing new features goes incredibly fast, but you burn through your credits even faster. You'll certainly be able to spend a while at this stage, and you'll definitely get results that go beyond what you could fix or implement by hand. In barely imaginable time, you've fixed the 3 big bugs and built the feature your customers have been waiting for so long. Compared to the results you get, the cost is easy to swallow, maybe even a bargain. But what about the documentation? What about the changelog? Have you also closed all the tickets you worked through? What about the website where you always publish the info on what's in the update? Oh, right. And the email notifications to your customers? Are you still writing those by hand? And what about the translation for the international update? And did anyone actually run a spell check on the email and the website? Do you answer all of these with no? Then there's even more potential. But first, we need to talk about the next problem, one that creeps in quietly. Yes, the agent can now compile through a tool reliably without guessing about paths, but that's where the next more subtle problem begins. And he just had room left in his context window. But then he reads that huge definitions file for the 7th time, and before you can even give another instruction, the auto-compact kicks in, which usually means he's unfortunately forgotten the instructions you carefully gave at the start of the session. The first things you optimize are the settings. How should he generate source code? So you create MD files for that. That works pretty well, and the source code starts to look better too. But as a small side effect, his context window is already smaller at startup. The auto-compact comes earlier and earlier, and token usage has gone up too, because he constantly has to read these MD files and also writes his memory into MD files. But since the quality improves, you ignore it for now. There are 2 problems, token burn and workflow. We must solve both. But first, we need to see just how deep this rabbit hole goes. In a typical setup, every session starts its own set of MCP servers. 5 open windows mean 5 running sets of servers, and each server first reports to the AI which tools it has, with names, parameters, and descriptions. That sounds harmless. Let's run the numbers. A realistic Delphi setup has a source code server, a document server, a code indexer, a file editor, and a few helper services. Together, that's quickly more than 150 tool declarations. Each declaration costs between 150 and 300 tokens. With 150 tools, that's 22,000 to 45,000 tokens of overhead before the AI has seen a single line of code. On top of that come your rules and all your settings. With a normal model, 20% of the context window is already in use. With a local model, it can already mean that the entire toolset doesn't even fit into the available context window. And if it does, there's barely anything left to even ask the model a question. That's the hurdle of stage 3. The AI finally has tools, but now it is buried under them. And finally, you may not want to work on just one project at a time. You might be fixing a bug in one window, revising the documentation interactively in a second, and already preparing the update emails in a third. But if every window and every agent has to load its own MCP server instance, memory becomes a problem very quickly. And of course, these separate MCP server instances know nothing about each other. So it is entirely possible that the agent in window 1 is trying to compile the application, while the agent in window 2 is still modifying a unit. There is no shared state, no coordination, and no communication between them. And then, once our free credits no longer cover our needs and we constantly have to buy more of them, the idea comes up. Local models. What is the GPU in your machine for? If not this. But this is exactly where the token overhead from earlier comes back to bite you. A local model has far less context, and the tool declarations we just calculated eat almost all of it. So before we can even talk sensibly about local models, we have to solve the underlying problem, that every window drags around its own mountain of tools. And that's exactly where the next stage takes us. Let's look at the 3 problems we have identified so far. Problem 1, 45,000 tokens of overhead. Problem 2, 5 windows, 5 isolated worlds that know nothing about each other. Problem 3, Markdown files keep piling up, consuming more and more context, yet still never get fully processed. All of these problems share a common root. The MCP servers run in the client, not in the backend. Every instance starts fresh, knows nothing about the others, and the agent carries the entire load around with him. The idea is simple. What if the MCP servers don't run in the client at all? What if there's one central server that starts once, loads all modules once, and then serves all agents, all windows, all sessions? Then there's no duplicated memory, no lost state, no more isolation, and the agent no longer sees all the tools at once, but only the ones he needs right now. And what is the effect? Most of the context window then belongs to your code again, not to the tool list. At the very top sits the AI agent. In the middle, a thin proxy, the only endpoint the agent ever sees. It contains no business logic. Its job is to translate messages and forward them to the backend, deliberately thin. At the very bottom sits the truly interesting part, the backend server. A Delphi application that loads a collection of modules as DLLs, manages sessions, dispatches calls, and holds shared state. There are three kinds of modules. Agent-side modules provide tools, MCP server DLLs, that the AI calls directly: read, write, compile, debug, search. Background modules work on their own, without any agent involved. And infrastructure modules provide shared services, such as the database connection. And this is where the real efficiency comes from. Each module is loaded exactly once. All sessions share the same heavy resources: loaded syntax trees, database connections, job queues. A new session costs a handshake, not a whole new process with gigabytes of state. And because every module is a DLL, the backend can be extended without a restart. A new module, just add it. An update, hot swap while the backend server keeps running. The system grows without interrupting the running sessions. The proxy layer solves the token problem in an elegant way. A single endpoint that always shows the model only the relevant tools and forwards the call to the right server in the background. The agent asks for what he needs and gets exactly that, nothing more. So 22,000 to 45,000 tokens of overhead turn into roughly 500 to 1,500 tokens. And this is the point where insight becomes a product. This proxy layer isn't a recommendation I'm giving you. It's architecture I've built. I call it ProxyMCP. ProxyMCP itself is always there, with a handful of its own tools, and those are the real trick. The agent doesn't have to carry the schemas of all those backend tools in its context. With list MCPs, he can list every server loaded on the backend and every tool. With dispatch, he calls any of those tools directly, and with explain, which I want to highlight in particular, he can get the full JSON schema of a single tool call exactly when he needs it, without loading it permanently into the context. And if a function is actually missing from an MCP server, he can file a feature request right away. So he has the entire backend within reach and still pays almost no token overhead. What gets loaded statically up front is controlled by a small ini file in the project folder. It bundles named toolsets, one set for Delphi development, one for blog work, one for documents. So each working directory gets exactly the tools that belong there. Everything else the agent fetches on demand through the proxy tools. With that, the system is operational, but still without memory. And that's exactly the next stage. The next module solves the Foundation's biggest problem once and for all, the missing memory. It's called PlanMCP. Anyone who works seriously with AI assistants knows the pattern. The session is going well, but the context window fills up. You write a summary into a text file, hope you haven't forgotten anything, and paste it into the next session. It works, sort of, but it's fragile and manual. PlanMCP replaces all of that. The state, task list, progress, decisions made, open questions, everything lives in a database, not in the conversation. That makes the command to clear the context window trivial. You just clear it. The next session reads a start prompt from the previous session, and the model is right back up to speed. This resume hint makes everything continue seamlessly, as if nothing had happened. That's exactly the difference between an assistant you constantly have to hold by the hand and one that carries a project for weeks. But PlanMCP can do much more. It's not just a file replacement, it's a structured project database. It holds tasks with dependencies, status, and owner, plus decisions with rationale, identified gaps with severity, stored artifacts, a complete event log, and whole documents with individual sections. Even every session is logged, so instead of crawling through one bloated MD file after another, the model now queries exactly what it needs, saving thousands of tokens and with them credits. And because all of it lives on your MySQL server instead of in the project directory, decisions can even be set and retrieved across projects and workstations. The next module is DelphiMCP. The most common reaction is, oh, so it can compile? Yes, but that's the most boring part. What's interesting is the access through the syntax tree, the AST. When the agent works with a unit, it doesn't get raw Pascal source. It gets a structured representation in which every node carries a stable identifier, a class declaration, a method body, a conditional block. Each is a named, addressable node. Behind it is the AST generator of my Delphi source code formatter. It can hold every unit and even the entire project in memory as an interface-based tree. I'm not talking about an agent crawling through 300,000 lines of source code to find a method or a definition. I'm talking about real-time access to your entire project, every class, every method. The agent doesn't say find line 817 and replace the third occurrence. He says replace the node with this identifier. That's unambiguous, and it works reliably even in a code base with 2,000 units, because it's not navigated by line numbers, but through a structured index. And how does the agent write code? The answer is simple. He only writes the lines that are pure Pascal. Structures like for, repeat, while, if, then else, as well as whole classes, he generates with a simple tool call and a bit of JSON. The code and the structure are written into the AST at the right place and, when the agent is done, written to disk through the formatter perfectly in the desired style. Borland style, my style, or your own style, exactly as you've defined it. There's an SDK for that. The syntax tree gives the agent structure. What it lacks is semantic understanding. The difference between here is a variable named sender, and this variable in exactly this call is of type TObject. For that, there's only one reliable source, the Delphi compiler itself. The LSP handler module connects to Delphi's own language server, the same one that drives the IDE's code completion and go to definition in the background. The two modules work hand in hand. The agent uses the syntax tree to change code and the language server to understand it. Together, he has the same combination a developer has in the IDE. Software development doesn't happen only in the editor. There are tickets, emails with requirements, Word documents with specifications, database queries for the live data state. Every time these things sit in separate tools, you become the manual bridge. Exactly the foundation's problem, just one level up. The integration modules close that gap. The agent reads and updates Jira tickets, reads and replies to Outlook emails, writes and formats Word documents. And through the MySQL interface, he has direct access to production data for queries, reports, or to store his own data permanently. Picture the whole workflow. The agent gets a Jira ticket with a reported bug. He reads it, finds the relevant code path through the syntax tree, makes the fix, compiles, verifies, closes the ticket as done, and appends a note to the release notes in the Word document. That's a complete development cycle, from bug report to close ticket and updated documentation, with you reviewing and approving, but without you carrying out the individual steps by hand. And now the module that will create the strongest reaction from experienced Delphi developers, the AI can debug. Not pretend to, but actually drive a real running Delphi debug session through the very same interface you use when you press F9 to run, F7 to step into, F8 to step over. And here's the twist that makes this module technically demanding. It supports both Delphi 2007 and the modern XE versions. Delphi 2007 has a different debug interface than XE. 2 different DLLs, 2 different protocols, but the same MCP interface upward. The agent notices none of it. He sets breakpoints, reads variable values, steps through the code, no matter which Delphi version is behind it. Of course, that doesn't just work without an interface inside the Delphi IDE, so I wrote a dedicated plugin for it. The agent can start Delphi himself, or he sends out a broadcast, "Hey, which Delphi version is currently running?" And the plugin answers, "I'm Delphi 11.3 and no project is loaded right now." From that point on, the agent controls not only the debugger but also the IDE, for example, to load the correct project. Honestly, I was skeptical it could be this easy, but when an agent, triggered by an incoming ticket, found the problem with the debugger in 2 minutes, I was convinced. The backend server doesn't have to run on the same machine as the agent, and that's exactly what makes it interesting for demanding tasks. A concrete example from practice: FFmpeg-MCP. The agent wants to render a video, but that's a GPU-intensive task that would block the development PC for minutes. Instead, ProxyMCP forwards the call to the machine that owns the GPU. Because my development environment runs in a VM, and a VM, as is well known, has no direct access to the graphics card, so FFmpeg doesn't run in the VM, but directly on the host, with full access to the GPU. The agent gets the result as soon as it's done. Where the PC with the GPU sits doesn't matter to the agent. An ini file specifies that the FFmpeg server is installed on the PC named GPU. The same principle applies to every resource-intensive task: compiling and publishing new project versions through a build server, speech generation through a text-to-speech server. ProxyMCP knows which backends are available and automatically routes to wherever the capacity is. For the agent, it always looks the same: 1 call, 1 result. That's the difference between a lone worker at a desk and a well-rehearsed team of colleagues that handles every task right where it belongs. The agent conducts, the team does the work. Or, to put it better, many PCs working together, collaboratively and agent-driven. Well, and guess how this video was made? Without editing software, without a graphics program. The source was just a script written in Word. It's probably needless to say that even the raw version of the Word file came 100% from the agent's knowledge of my projects. Sure, I added a few paragraphs and had to adjust some of the auto-generated text here and there. But you don't really think I typed those changes in Word, do you? After an initial review, I worked through the text paragraph by paragraph with Opus and made corrections. For the English translation, I refined many of the phrasings. Finally, each paragraph's text-to-speech output was checked and occasionally corrected. We already talked, back in stage 3, about the fact that local models have their own limitations. What we haven't talked about yet is the procedure for actually making local models usable for our agent in the first place. There are several options for this. I decided for once not to implement it myself in Delphi, but to use the proven Ollama server, even though a proof of concept written in Delphi had already worked. Apart from the cost savings, an important point for many is also GDPR. Some data isn't allowed to leave the country, other data not even the company network. This is exactly the gap that local models close. The backend server has gained an Ollama service. This one, for a change, is not an MCP server. The Ollama module provides its own job queue for batch work and a GPU guard that checks utilization before it can start a task. What's the difference? I don't interact with the local models in a back-and-forth dialogue the way I would with ChatGPT or Claude, the way Kai does, for example. I only use the local models for specific tasks. Let me give you an example. The task is: give me an overview of what these 1000 Delphi units do and condense that into a short evaluation. I certainly don't want to run that task through a cloud provider with token costs, especially not if I want to start it overnight with 20 different tasks across all 1000 units. Exactly how that works, I'll explain later, because for that we still need 1 or 2 more modules in the backend server. But before I can say which local model is best suited for what, I need to know what the models can really do. And I measured that with a great deal of effort. For that, I recommend my 3-part blog post. For the benchmark, I ran 8 local models through 5 task phases, with 30 real Delphi production units. The 5 phases reflect what a real Delphi assistant has to be able to do. First, find hidden problems before you touch anything. Second, understand what a unit really does. Third, write correct Delphi code, not just plausible-looking code. Fourth, judge when a task is trivial and when it needs a stronger model. And fifth, tool calling. That's the part that shows whether the model can handle an MCP server cleanly and pass the correct parameters with the correct data. I don't want to go through all the numbers, but there are 4 findings you should know because they shape the entire architecture that follows. First finding, there is no universal winner. Strong code comprehension and strong patch generation do not automatically come from the same model. In my case, ironically, the best patch generator had the weakest comprehension score. These are clearly different capabilities. The consequence is routing. Each task type should be handled by the model best suited for it. And that's exactly how the pipeline is built. A fast router model looks at each task and decides, is it trivial, medium, or hard? Trivial goes to a fast model, hard to the best comprehension model. Second finding, and this one is brutal. Tool calls are a yes or no capability. A model either returns clean JSON objects or it just outputs text. Several otherwise capable models failed completely here at the API level, not fixable with better prompting. For any pipeline that talks to an MCP server, this is a filter that applies before anything else. Third finding, and as a German-speaking developer, especially interesting to me, every model performs worse on German prompts than on English ones. For tasks involving code, the loss reached up to 31 points. The practical lesson: use English for anything that contains code or asks the model for specific identifiers. Use German for everything that faces the developer, the interface, and the explanation. Fourth finding. I additionally ran the same 5 phases on a strong cloud model as a reference point, and here's the honest answer. In intuition, routing, and tool calls, the local models are practically on par with the cloud. There's exactly one real gap: the deep understanding of code. There, the cloud model is about 28 points ahead as of June 2026. That's the only phase where local models clearly fall behind. And that's exactly what dictates the architecture. A team with strict data protection requirements can stay entirely local. Anyone allowed to work hybrid sends the tasks that require deep code understanding to the cloud and keeps everything else local. Both are a deliberate blueprint, not a workaround. At the very top, 3 modules work together. The scheduler can start tasks on a timer, every 3 hours, once a day, every Tuesday. With that, it launches the tasks through the Orchestrator. The Orchestrator manages the recipes for the tasks through the MySQL interface. The third is the runner. It makes sure the data is generated or stored. The runner is a collection of Delphi jobs compiled as a DLL that the Orchestrator can call. A concrete example: the scheduler runs every 3 hours and gives the Orchestrator the command mailCheck. Through the internal dispatcher, the Orchestrator calls the job readMail IDs in the runner. This method reads the last mail ID from the MySQL server and then checks via Outlook MCP whether there are new messages. For every new email, the runner queues a single job in the Orchestrator. Read mail by ID. The Orchestrator starts the queue and runs the individual jobs through the runner. Read mail by ID reads the mail and returns its content and a prompt to the orchestrator. The recipe contains two tasks. First, classify spam or a real email. Second, assess how important is the customer message. The router model determines the right model. The task goes through PlanMCP to that model. Depending on the answer, the right job is called. Either the message moves to the spam folder or a ticket is created via Jira MCP. That's what I call efficient use of local LLMs. And one more detail I don't want to leave unmentioned. For the jobs that are built into the runner, I didn't write a single line by hand. I just enter the prompt. One model generates the code, another model checks the code with the compiler via DelphiMCP, a new runner gets installed and hot swapped into the backend server. And there is a part that runs entirely without you. A scheduler fires at a fixed time of day. It triggers the orchestrator that picks up open analysis jobs and hands them to the local model. The results flow into a code knowledge database. The database grows with every run. The next time the agent has to understand a part of your codebase, the answers are already there. No prompt, no developer at the desk. Software that quietly, reliably builds something useful in the background. And that is exactly the difference this whole video is about. None of this is something you get with prompts, no matter how well they are written. Prompts are volatile. They vanish when the context window is cleared. They can't set a breakpoint. They don't remember the architecture decision from last week, and they don't run at 3 in the morning when no one is watching. The real leap doesn't come from a smarter prompt. It comes from treating AI as a component inside a well-designed system architecture, with state, with typed interfaces, with a life cycle, and with a connection to the real tools. Hey, great that you stuck with me all the way here. This was the path from copy and paste to real enterprise workflows in 14 stages. If this was useful to you, but you're not sure how to adapt it for your own setup, there are 2 ways. Way 1, do it yourself. For that, I've set up a shop on my homepage. There, as of May 2026, you can order the modules shown here as Delphi 13.1 source code. Note, the Everything module needs the Void Tools search tool installed, and DelphiMCP and Pass Indexer also need a DLL, which is included in the bundle. These are the standalone modules from Stage 2 in version 1.0, and then there's the second way. My backend server has evolved well past what you see here, as of May 2026. Its architecture isn't just an entry point for individual developers, it's also built for teams and distributed resources. The backend server hosts the MCP servers you can see here. The server needs access to the source code, so there are 2 options. First, installing the server right where the source code lives, and second, using the remote file server. The possible combinations are too many to explain in detail here. That would go beyond the scope of this already too long video. That's why for now, my homepage simply says, Price on Request. I'm currently preparing the complete ecosystem of MCP servers and backend modules, and since no one wants to configure all of that by hand, I still need to build a smart installation process for it. Maybe in one of the next videos, I'll show how the same backend server works not just for a single developer, but for an entire team, with shared state, with role assignment, and with parallel agents that genuinely work together. If you like my videos, please hit the like button and don't forget to subscribe to my channel.
There's a fire burning out on the street. I can't bear this heat. You claim it was my fault, but I know it was you still hiding the truth.